Okay, hopefully that's better. Yeah, so I'd like to kind of show you a couple demo searches to make the rest of the talk a little less abstract. So we're going to take a look here at this interface. So Cochlea is this prototype search that I've built. Right now it only indexes over about 70 hours of audio, which, depending on your perspective, is a lot or nothing. If you consider the fact that there are, I think, like 300 hours of video uploaded to YouTube like every minute of every day, it's nothing. But if you're like a sound designer or a musician who has a large corpus of audio that they're working with, and they don't necessarily want to annotate all of that by hand, this could be potentially a useful tool. So to illustrate kind of like what I'm after with this search, I was going to demonstrate a couple. Really what I want is something where I can search by perceptual similarity. And I also want to be able to pinpoint relevant moments in sound. So I want to take a segment of audio as a query, and then I want my results to tell me not only what files contain relevant content out there on the internet, but also like where in those audio files the relevant content occurs. So one of the data sources I used for this is Internet Archive, which happens to have like a lot of like hip hop mixtapes on it. There's this artist Chance the Rapper that has some audio out there on Internet Archive. There's this one song that happens to be kind of like an atypical for a hip hop song, and then it's got quite a bit of piano and strings in it. So if I were doing a purely text-based search, this would probably be labeled as like hip hop or rap potentially, just based on the context, the artist, etc. But there's this kind of moment in the middle of this song where there's kind of this nice little piano break, and I get this little link from Cochlea that says sounds like, so that segment that I've just clicked on and played, got a link that kind of is going to take me to hopefully, perceptually similar segments elsewhere. And what I end up getting when I search by that is some segments of audio from some classical piano pieces, which here are some segments from that original piece of audio, some more pieces of classical music. We'll just do one more really quickly. So if I start with a text search for speech and listen to a few audio examples.
By the police.
Excuse me if the volume is a little variable. If it gets too loud or too quiet, just let me know. So I can listen to
Rise again.
Some of these
Rise
examples.
Again.
And again, if I take this sounds like link and use it, hopefully I'm going to find some interesting results. So it looks like actually that first one was not really what I wanted.
It will rise again. It will rise again. Again. And dragon.
So here you can see
again.
That we've gotten quite a few results from the same file. What's interesting is we've also got
rise again, and dragon is
got some results
it will rise again
from another file with the same speaker. So he's got sort of a similar like intonation, saying some similar things.
Wait, so you shouldn't have too much.
And if I continue down here, I might see continue.
Ascribe to him.
This guy happens to have uploaded a lot of audio files of himself speaking on freesound.org. And then finally here we've got some segments from Martin Luther King's speech as well, if they load.
And the Negro boys, but it is.
Oh, yeah, there you go.
And the Negro boys and girls.
So the idea here is that we're using a segment of audio as our query, and hopefully we're locating some relevant moments in other sounds, regardless of whether those sounds have been tagged with text or any other human annotations. So that is kind of a quick quick demo for you, and there are some more. If you the slides are on meetup.com, and there's some more example searches here if you'd like to just some starter searches to find some kind of like areas of audio to explore. So the outline of the talk. First, I'll try to answer the question like, why would I want to bother to even do this? Next I'll kind of review the paper that kind of gave me a good direction for how to train a model to do this, called Unsupervised Learning of Semantic Audio Representations. I'll talk a little bit about the data sources I used, a little bit about my model architecture, which is incredibly boring and not exotic, because it was kind of the least interesting part of this whole process for me. I think there's a lot of fertile ground for further exploration there. I'll talk about the training procedure, and then I'll talk about, how do we index this data? How do we search over it relatively quickly? And then a quick peek at the production architecture for this. This is still a very small kind of toy app, so that's not going to be particularly interesting. So the first question, why bother to do this? Obviously, there's a ton of audio out there on the internet. Most of it unlabeled or poorly labeled. I think it's a potential, untapped resource for musicians and sound designers, anybody who's doing like sample-based work, who wants to be able to like search over audio in an intuitive way. Most searches that are out there are based on text descriptions or tagging, which tends to be kind of noisy and subjective, and with the exception of Freesound, which I gotta kind of give them props for their similarity search, which works pretty well. The one thing it's missing, in my opinion, is the query is an entire, the atom there, the atomic unit is an audio file. So it doesn't matter how long the file is, right? The query there is an audio file, and the results are audio files. But in general, like, if the audio file is 2 hours long, it doesn't really help me much. I want to know, I want timestamps for like relative segments in the audio. So this paper, Unsupervised Learning of Semantic Audio Representations, presents this very kind of simple approach. This paper comes, from Dan Ellis's research group at Google. Dan Ellis was also pretty influential in creating the librosa Python package, which is a pretty popular package for doing like music information retrieval in Python. So if you've ever run into that library or used it, this is some research by one of the authors of that library, which happens to be really great. So the key sort of observation that they make at the beginning of this paper is that there are certain deformations or transformations of audio that don't change like the class of audio that we perceive. And I could kind of just read this list off, but instead of doing that, I have this quick little demo here that'll kind of give you a better idea of what this means. So given this original file of like a, can everyone hear that okay? Okay. So if I shift the pitch of the sound like up or down, the texture is still the same, like the class of the sound is still the same. If I sort of like compress or dilate the duration of the sound, again, within some reasonable bounds, like if I do that, I'm still getting like the same texture, and like perceptually that still falls into the same class for me. The next one that they call out is not really a deformation or transformation, and in my opinion, this is kind of like the most interesting one. It's just temporal proximity. So basically it's saying, sounds that happen near to one another in time tend to be, semantically related to one another. This, I think, has a strong similarity to a lot of the techniques used to learn word embeddings, which is basically just saying like, hey, these words have some kind of like semantic similarity based on like their co-occurrence, frequencies in this like large corpus of text, as an example. And I have this suspicion after working through this project that temporal proximity might be the only thing you need to really train one of these models, because you tend to have some of these same kinds of transformations happening over time to an audio signal. Like, music will sort of change pitch over time without changing the sort of texture. So I'm curious to try training with just the temporal proximity deformation. But they also call out additive noise, which might be hard to hear in here, but there's just some Gaussian noise added to the signal. It's just kind of staticky. And then they talk about mixtures of sound. So if I take a flute and drums and then add them together, right? Like, I'm going to tend to assign that to both classes. It's like, woodwind or flute class and drums, since they use the word like transparency to describe like what happens when you add audio together. You can hear both of those sounds fairly well together and kind of identify both of them clearly and separately. So what they're going to do after making that observation is try to learn some mapping G that's going to take input samples in this frequency times time dimensional space. And we'll kind of get more into why it's sort of written that way. It was a little strange to me at first as well, but this input space and maps it into this lower dimensional embedding space where hopefully, something like Euclidean distance or cosine distance in the target space can map to these very complex transformations in the input space. Hopefully some of the deformations that we just listened to perturb the data point in the embedding space very little, right? Like pretty large changes in the input space, but they should move the target embedding very little. So our training data is just going to take the form of in triplets, and each triplet is going to consist of an anchor example, a positive example, and a negative example. So we're going to choose a short audio segment at random as our anchor. To derive like a positive example, we're either going to choose a segment that occurs near in time to that anchor in its source audio file, or we're going to apply one of those deformations, right? We're going to take the anchor and shift its pitch up or down, or stretch it a little bit, or add some noise, and we're going to say like this positive example is semantically similar to our anchor. And then finally, provided we have a large enough data set, we're just going to choose our negative example at random. We're just going to go pick another segment from our data set as our negative example. So you can see, obviously each of the anchor positive and negative is going to belong to this input frequency times time dimensional space. And ultimately what we're trying to get our network to do, and I guess I failed to mention here, G, this mapping in this work just takes the form of a neural network with learnable parameters, right? That's what we're after. So we would like the distance between the anchor and the positive examples to be less than the distance between the anchor and the negative examples by some margin delta here. And then this little plus sign in the bottom right-hand corner, this is sort of the notation they use in the paper, indicates that we're doing like hinge loss, which means that if we're below that margin, the loss is just gonna go to 0. So basically, put another way, we're trying to get our network to, push these anchor and positive examples close together in the embedding space and push the anchor and negative examples far apart in the embedding space. So digging a little deeper into what we mean by this frequency times time dimensional input space. In the paper, the input is something they call log scaled MEL spectrograms, and we'll talk in detail about what that means. But this sort of like purplish image here is a spectrogram with time along the x-axis and frequency bends along the y-axis. And then we're going to be trying to map into our d-dimensional space, into our embedding space. So I've got this kind of Jupyter notebook to just kind of walk you through what this like log scaled MEL spectrogram thing means. So we're going to start by just like downloading some audio from Internet Archive, and then we can quickly just look at the raw audio samples. That one's pretty loud, sorry. So anyway, there are the raw audio samples of this Bach piano piece. The time frequency representation that everyone's probably most familiar with is the short time Fourier transform. How many people in here know what that is or are familiar with that? So yeah, I mean, in general, you're just going to be, it's pretty common in audio. You're going to be taking these short, about 40 millisecond overlapping windows of audio and performing a Fourier transform of each of those windows. So you're going to get decent frequency resolution within those windows and good time resolution over the course of the audio file. Like as the signal changes, as the frequency content changes, by taking successive Fourier transforms, you're going to get, a good notion of where in time those frequency changes are occurring. So the problem with this really commonly used transform is that it kind of ignores some things we know about human audio perception. And so what they're after in this paper is an input that does some things that approximate some pre-processing that happens in the human auditory system. And there are really two important things there. One is that we tend to perceive frequency on a roughly logarithmic scale. So if you were to plot like the notes on a piano as you played them, the frequencies in hertz would get successively further and further and further apart as you made your way up the keyboard. So here we just got this linear frequency axis for the FFTs that runs from 0 hertz to about 20 kilohertz, which is the upper range of human hearing typically, and then this MEL scale or logarithmic mapping, where you can see that frequency resolution tends to be a lot better in these lower frequency bands and gets worse and worse in the upper frequency bands. And there's this inherent trade-off between how accurately you can measure frequency and how accurately you can locate things that happen in time. And our ear our auditory system tends to kind of do that. We have pretty good frequency resolution and pretty poor time resolution for lower frequencies. And we have pretty poor frequency resolution, but pretty good time resolution for higher frequencies, which kind of makes sense. So we can produce this matrix, which we can use to, if we take the dot product of this with every one of our Fourier transforms, we can kind of map those frequencies onto this MEL, this logarithmic scale. And so now you can see that the energy in the signal is kind of like occupying more of this frequency space. Excuse me. And another way to interpret this is just that, So the next thing that the Fourier transform doesn't take into account is the fact that we also tend to perceive loudness on a logarithmic scale. So once we've done that, then we're going to compute something like decibels from the raw audio magnitudes. And another way to interpret this, if you think about like the convolutional kernels that you use in your work every day, you can kind of interpret that almost like a bank of finite impulse response filters. So you can imagine instead of initializing those weights randomly, designing a bank of filters that map onto this MEL scale and make sort of a conscious trade-off between time and frequency resolution at each frequency bend. So here, you can see we've built this filter bank. We're going to visualize just a few filters here, those, going from lower to higher frequency. Then you can visualize the whole filter bank, which looks kind of trippy and cool. And then, we can use PyTorch here just to treat that as our sort of like convolutional weights, convolve it with our raw input signal, apply this log magnitude scaling and temporal pooling over 40 millisecond windows. And then we get a very similar looking time frequency representation. You'll notice that like the lower frequencies are a lot crisper here and less like blurry. That's because we've made, instead of kind of cheating and taking the linearly spaced FFT frequencies and then just like mapping them onto the MEL scale, we've made some really conscious choices about the time frequency resolution trade-off for each filter and convolved it with our input signal. That may be like more than you ever wanted to know about what MEL scale or log spectrogram is, but there you go. So the paper uses the ResNet 50 architecture. I'm not going to go super in depth into what that means or what that is. Probably most of you are familiar with that. I did not use this architecture myself. It was kind of the least important part of this whole process for me. You know, the training procedure seemed much more interesting. One other interesting sort of technique that I wasn't familiar with, some of you may be, that the paper introduced to me was this notion of within batch semi-hard negative mining. And I've got another quick little notebook here to demonstrate what that means. Really what it boils down to is, you know, in practice, since we're just choosing negative examples at random, and we've derived our positive examples by transforming our anchor in some way, in general, the negative examples are just going to be too easy. What happens, since we're using that hinge loss, is that our loss is going to go to 0 if it's below this margin, which means our gradients are 0, which means, you know, we're not updating our weights. So, you know, we're making life too easy for our model early in the training phases. So what we're going to do here is try to be very purposeful about how we construct batches of data so that we make life a little harder for our model during training. Doing this over the entire data set at once would obviously be the ideal, but since that's prohibitively expensive, what we're going to do instead is choose mini batches at random. And so here I've just got some code that produces some like synthetic data representing our anchor positive and negative examples. And then the paper goes on to say, like, we're going to choose the closest negative to the anchor that's still further away than the positive example. And so what we're going to do is within the batch, we're going to, so here this is synthetic data, and so you can see that the anchor to positive and anchor to negative distances are kind of occupying the same space. In practice, you would see generally the anchor to negative distances being quite a bit more. I'm sorry? Can I make it bigger? Okay, sorry. Yes. Well, so I'm just going to skip over that graph because it's probably shouldn't have been included and isn't particularly meaningful. But what we're going to do is within the batch, we're going to compute the pairwise distances between all the anchors and all the negatives, and that's just like a plot of this, you know, distance matrix here. And what we're going to do is use that distance matrix to reorder the negative examples such that within our batch, we're going to match up the negative examples as closely as possible to the anchor positive distances. So one way to think about this is that our network is constantly trying to widen the gap between the anchor to negative and anchor to positive distances. So we're going to construct our batches kind of in an adversarial way such that we're going to make the batch such that the negative examples are as close as possible to the anchor. We're trying to build batches that are as difficult as possible for our network on each iteration. So we're using cosine distance in this case. The embeddings are always going to be like on the unit sphere, and we're going to be using cosine distance to measure the. Correct. Yeah. So we'll actually look at an example code that'll hopefully make that more clear in just a couple slides. So that's the kind of this technique. So when I first started, you know, training, I kind of missed this detail, and I was just sort of choosing negative examples at random, and I noticed that my loss was going to 0 pretty quickly. It's not super helpful. This has been kind of key in, like, you know, constructing more difficult batches of data. So the paper uses AudioSet, which is this data set from Google with like thousands of hours of like annotated YouTube videos. I did not use AudioSet. I was also kind of interested in starting to try my hand at like scraping audio data and collecting data from more diverse sources. So I kind of pulled some data from different places on the internet. Internet Archive obviously has tons of good data. MusicNet is a good data set of like classical music. Freesound.org is a site that allows users to just upload audio content, and they've got a ton of good content there. And then there's Fat Drum Loops, which is what it sounds like. So my model is, dead simple, probably like brain dead, right? Like I wasn't super interested in the model architecture for this kind of iteration. So this is just like a very sort of standard 2D convolutional operations alternated with pooling operations with a global average pooling at the end, and then a linear transformation into the 128 dimensional embedding space. I'm also pretty resource limited at the moment, so this model has 2 million parameters, ResNet has 25 million, so that's a big difference. It'll be definitely interesting in the future to try out larger models. So really quickly, we'll just kind of look at the model code here. Again, I'm using PyTorch for this project, so I've got this embedding network class that inherits from the inn.module class. You'll notice here that I've got this filter bank that I talked about in the log-scaled MEL spectrogram notebook right here in the network, and that's actually happening in the forward pass of the network. I'm doing that for a couple of reasons. First is that I wanted to make sure that the interface for this just accepted kind of raw audio samples, because I think there are some interesting other networks to try out that might operate just directly on raw audio samples. So I kind of wanted the interface to kind of already look that way. Also, I believe in the paper they're performing these deformations in the spectrogram space, and I was a little suspicious of that. So I wanted those spectrograms aren't invertible. I can't get back the raw audio from the spectrogram because I've thrown a lot of information away, and I wanted to make sure that the deformations that I was performing like sounded natural to me, and there was no way that I could, you can just do translations and stretches of the image, but I was a little suspicious of that. So for those two reasons, I decided to just compute the spectrograms in the forward pass of this network. The weights of that filter bank are frozen. They're not learnable. Might be interested to make them part of the learnable parameters. You might end up getting better performance that way, but for now, they're exactly the same weights that we saw in the Jupyter notebook. They're just kind of hard-coded to be along that logarithmic MEL scale. And then here you can just see this is our sort of alternating 2D convolutions and max pooling operations. So our forward pass really is just like, we're gonna give example-wise standard deviation of 1 to all the inputs, because basically what that's saying is like, I don't care about the volume of each of these examples. I'm not sure that's the right answer, but that's what I'm doing for now. I'm gonna compute the spectrogram here, and then do my temporal pooling where over those like 40 millisecond overlapping windows. Then I'm gonna sort of like transform, so PyTorch's convention is, for tensors is, batch dimension first, followed by channels, then followed by, height and width for a two-dimensional image. So I'm gonna, add this additional dimension to the tensor, then apply my alternating convolution and pooling operations and my leaky ReLU nonlinearity, and finally do my global max pooling where I take the feature map down to basically size of 1, and then apply this linear transformation, and then give batch-wise unit norm to those embeddings, because again we're going to be doing cosine distance, so we're going to put all the embeddings on the unit sphere, and we're going to be looking at the angle between those embeddings. So let's see. So we'll look at a little more code. So The first thing I'll look at is just kind of, this sort of main entry point. So here's kind of where we're getting everything set up. We're kind of deciding we're going to resample everything down to the ridiculously low sampling rate of like 11.025 kilohertz, which loses a lot of the higher frequencies, but in practice hasn't seemed to matter a whole lot. I'm using Zounds, a library that I'm the author of and probably the only user of in the world, to create like a processing graph that's going to take sort of audio from the internet and resample it to this common rate. We're going to determine what our sort of audio segment size is. At this sampling rate, 8,192 samples translates to about 3/4 of a second of audio. The paper is using like 1 second segments. Then we're going to decide what we consider to be temporal proximity. So we're going to say anything that happens within 10 seconds of the anchor segment could be considered as a positive example. We're going to define the deformations that we're going to use. And then we're going to set this up using Zounds such that when we do all our pre-processing and downsampling of the audio, all that stuff's going to get stored in a local LMDB database. LMDB stands for Lightning Memory Map Database. It's just like a really simple, easy to use, embedded key value store database that happens to be pretty good for like storing lots of binary data. Then we've got some kind of your typical command line arguments like batch size and how often we want to checkpoint our model, like save the weights to disk. And that's not super interesting stuff, but this is sort of the framework for this. We've got this file that computes the deformations. So we've got our additive noise here, a time stretch deformation, which is going to either lengthen or shorten the audio, and then is going to perform either zero padding or truncation of the signal to ensure that it's still that 8,192 sample length. And then also a pitch shift operation, which is going to change the pitch of the audio, but not its duration. So then we can look really quickly at how the triplets are sampled. So this triplet sampler class is really responsible for mining these triplets from our LMDB database. So at the, for each batch, we're going to choose which deformation we want to use for that batch, kind of at random. Then for each element in the batch, we're going to choose an anchor sound and a negative example at random. If we've chosen temporal proximity, we're going to go and find a segment that occurs near to the anchor in time. And then, finally, if we have chosen something else, we're going to apply the deformation, and then we're going to kind of package it all up into a batch. And we'll be doing the hard negative mining part later, since we're going to have to actually compute the embeddings before we can do that. Finally, we can just look at what an individual training step looks like. This batch queue class is only interesting in that constructing these triplets is somewhat computationally expensive, in that we're doing time stretch and pitch shift operations. And we want to make sure that our GPU stays busy. So this is going to be, mining triplets in a separate thread, so that our main thread kind of always has pre-computed batches available to it, and our GPU never is just sitting idle waiting for a new batch of data to train on. And then really the interesting stuff in the training method is this main loop, where we're going to grab an example from our batch queue, move it on over to a PyTorch tensor and onto whatever device we're using for training. We're going to split out our anchor positive and negative examples, compute the embeddings. So this is kind of the part that you were asking about. So we're going to compute all the embeddings. And at this point, this is where we're going to compute the pairwise distances between the anchor embeddings and the negative embeddings. And we're going to return from this negative mining method, we're going to return hard negative indices. And then in this line, we're going to use that to reorder the negative embeddings such that they're paired semi-optimally within that batch. Then we're going to compute the loss here. And the loss we're using is this triplet margin loss, which is included in PyTorch. We're using Atom as our optimizer. And then we're going to, compute the gradients here, and then let our optimizer take a step in the direction of the gradients and update our weights. So pretty standard stuff there. Any questions so far, or anything unclear? Everything? Oh, our training examples consist of these triplets. So we're gonna, an anchor is sort of an example that we'd like to take a positive example and move anchor and positive examples close together in our embedding space, and we'd like to take anchor and negative examples and push them far apart in our embedding space. And that's kind of the technique we're using to learn these embeddings in an unsupervised fashion, like without any extra annotations. So finally, the question is like, okay, like we've trained our model. Hopefully we've got decent embeddings that capture some kind of notion of semantic similarity. So now the question is, how do we search over this? I think there are better techniques out there than the one I'm using, and it's a good area for exploration. Spotify has this cool library that I just found recently called Annoy that has a lot of different techniques for doing approximate nearest neighbor searches, which I'm going to be looking into soon. But the route I took to speed up the searches a little bit was something called random projections. And this notebook will kind of walk you through what that means exactly. So if we start from like a toy example, where we've got, instead of 128 dimensional embeddings, we've just got 2-dimensional embeddings on the unit sphere. It's going to look something like this, right? So we've got these data points. If we want to characterize those data points or like approximate their location, one way we can do that is by sort of slicing up that space with some random planes. So you can see here we've got all these different planes that are going through the origin and sort of dividing up this space. So we can then like characterize a data point with a number of bits that is equal to the number of planes that we've chosen, where each bit is on or off based on which side of the plane that data point lies on. And the reason we would want to build these bit vectors or bit strings to approximate the location of those elements is that we can then do a really fast, like brute force kind of Hamming distance search over this index, using sort of like bitwise XOR and then bit counting instructions, like processor instructions. They're going to be a lot faster than doing the brute force cosine distance search. So then if we look at a more realistic example where we've got, 500,000 examples, which represents about 100 hours of audio given our segmenting scheme, and we're back up to our real world 128 dimensional embedding vectors. I don't know why I felt the need to graph a bunch of random noise there, but there you go. So now we want to look at what the speed and accuracy trade-offs are. And we can imagine a few different ways of doing the search. We can do a brute force search, which is probably going to be slow, but obviously, perfectly accurate since that's our ground truth. We can imagine just using this index of bit vectors that we got from our random projections. And then we can also kind of imagine a hybrid approach where we use the index of bit vectors to kind of narrow the field and then perform brute force searches within that subset of data. So this notebook kind of just sets up a bunch of code that makes it possible to run those experiments and do some timings and compare the accuracy of these different techniques. And I won't bore you with all this, but really this is where the rubber meets the road, and make sure everybody can see that okay. Ultimately, you can see the little red square in the bottom right-hand corner is the brute force search. So we're doing like maybe like 10 queries per second over our 100 hours of audio with perfect accuracy. Sorry, I'm gonna make this try to get this to fit. So if you look at the blue line, that's just using our random projection. So that's just doing the bitwise kind of Hamming distance. You can see that that's really fast, but it doesn't really matter because we never get better than like 50% accuracy or like overlap with our ground truth, even when we're using like 2048 hyperplanes or 2048 bits. The sweet spot seems to be in this hybrid approach where we use the bit vector index to narrow the field and then use the brute force search on that subset. So there seems to be this kind of sweet spot like around maybe like 512 hyperplanes and hence bits where we're getting like maybe 50 or maybe up to like 70 queries per second, somewhere in there, and getting like 90% accuracy, which is probably like pretty decent. This is really just an object lesson for me and why you should measure a lot, because I measured this once a long time ago and thought I remembered how everything worked. And so the site, the demo we looked at, is actually only using this random projection method on its own because I thought it was good enough. It's fast, but it kind of sucks. So in making this Jupyter notebook, I realized like I've been wrong for like 3 months about how this is working. And so now I'm gonna have to go back and add in this hybrid method. So don't do just the random projections on their own because they don't seem to work super great. So that's almost all I've got. The production architecture, super straightforward. This is all living in AWS. So when I post a new sound to this cochlea.xyz app server, what that's going to do is put some metadata about the sound in this Redis queue here. And then there's just another EC2 instance running that's going to compute like spectrograms, transcode audio, and do model inference. So we're going to do model inference on the CPU on this EC2 instance to compute our embeddings. And when we're done extracting all the features, like the text features are going to go into Elasticsearch. The embeddings and the bit vector index is going to go into this other EC2 instance, which is just doing perceptual similarity searches. And then, the transcoded audio and spectrograms are going to go into S3. So when I perform a query, I'm either going to be asking Elasticsearch for answers if it's a text query, or I'm going to be asking the similarity index for answers if it's a perceptual similarity query. So that's what production looks like right now. Finally, I'll just talk about some future directions or things I didn't get to try for this talk that I really wanted to try out and will be soon. So with word embeddings, there's this classic example that I'm sure everybody's heard of, like king minus man plus woman equals queen. I'm really curious to try out some of those vector arithmetic examples with the audio embeddings. Like if I take, speech embedding and drums embedding, can I like add them together and get like something in like a hip hop kind of space? Or can I add instrument embeddings together to get instances of those instruments playing together? Can I do meaningful things with these embeddings? Another one is like using the embeddings as a conditioning vector for like a WaveNet or generative adversarial network type model. Like if I've got this embedding that captures some kind of high-level semantic notion, could I build like a synthesizer that's going to produce realistic audio that's like, hey, this sounds like jazz piano or something. And then finally, probably the most practical one is just, can I use these embeddings to predict labels for unlabeled audio? Like, can I just use it to annotate stuff that isn't already annotated to make text search better? That's it. Thanks for listening. appreciate you bearing with me, and sorry if that ran a little long. I don't know. So yeah, any questions are more than welcome. Yeah. So the question I think was, did I try clustering, like a k-means kind of like clustering approach? You know, no, but that's been on my mind, and I've been thinking about that might be a better direction to go. Is just, you know, choosing a number of clusters and then given a query, kind of like find the cluster that's nearest, and maybe some kind of like hierarchical clustering kind of approach might work well. Yeah, that's a great question. Okay, yeah, KD tree. Yeah, I think I'm familiar with that, and definitely another good one to try. Oh yeah, so we talked about kind of like computing these embeddings and the possibility of just like doing brute force search, and then we talked about using random projections to come up with those bit vectors that you could use to search over for approximate k nearest neighbors. So that similarity index right now really just has that index of bit vectors. So when I perform a query from the front end, it's really just coming into that similarity index as like, here's this long bit string, perform this like brute force Hamming distance query over everything, and return me like, you know, the IDs of the relevant. I was only curious, I did something very similar for images. Okay. I have heard of it now that you mention it, so yeah, I will go check that out. Okay. Yeah. That's a fantastic question, and I mean, like, I think I'm supposed to repeat the question, right? Like, the question is just like, you know, how do if I'm making changes, how do I know it's getting better? Well, like in this case, like, you know, what does semantic similarity mean? It's a really good question. I mean, honestly, I think the ultimate answer is going to be having more users beyond just myself. It's, you know, and I don't have a good sort of objective way of measuring that, or some benchmark to say like, this is improving. I mean, my intuition is training on more data will help. Oh. Yeah. So I have a very informal technique I use by which I kind of just call the like, how often am I surprised? Where I'll kind of like listen to many examples, and I kind of take note of like how often I'm unpleasantly surprised by a particular search result. And sometimes, given enough of those, I can come up with some kind of hypothesis about like what's wrong with the model, or how I might tweak the model to discount or highlight that particular feature more. But yeah, it is very touchy, like it is very subjective and not kind of mushy. Yeah, I mean, I think that, what I always start with is, like, I always start with the brute force search, so I know I'm working with the ground truth, and I listen to examples of that, and, but then, yeah, there's this whole other variable you bring in when you're like, okay, now we're going to bring in this approximation of, the brute force, kind of ground truth search, so. Oh, yeah, good question. So, yeah, sorry if that wasn't clear. So what I mean by accuracy is doing the brute force cosine distance over the entire data set is obviously the right answer. So accuracy basically just means like, what's the intersection between the result set returned by the approximation and the result set returned by the ground truth. So I'm basically just saying like how many of those search results did we return in common, given some like search results set size of 25. Like how many of these results are shared by both the approximation and the ground truth. I'm not actually taking the order of the results into account, like in terms of relevance. I'm just saying like, hey, what's the intersection of the set of results at this time? So. Right. You mean the number, like the size of the? It's not a classification layer. It's like a dense vector, and I honestly just picked that because that's what they use in the paper. There's no particularly good reason for choosing that size of like dimensionality for the embedding. I don't know. It would be interesting to try other like dimensionality for the embedding. The paper used 128 dimensions, so I was like, sure, why not? No, it's not. It's not a classifier. It's a sort of like continuous 128 dimensional space. I am forcing all those to live on the unit sphere in that space. So they all have like unit norm, I guess. But yeah, it's just a continuous 128 dimensional space. Well, so CDist is actually, I'm only using when I'm doing the within batch negative mining just to compute that distance matrix. So I'm not using SciPy's CDist for the brute force distance over the whole data set. I am just using it right now for the within batch negative, within batch semi-hard negative mining is what they call it. But yeah, I am interested in looking into that. Yeah. I think you had a question, maybe? I would love to talk to you about that because I kind of looked into some techniques for doing that, and it was never clear to me like how exactly to use Elasticsearch directly for that. I know it supports has some geospatial support, but I didn't realize it had like support for dimensions greater than 3, I suppose. That would be super cool. Cool. Well, thanks.
All right, everybody, that concludes our evening. Let's all go to CU29, but unfortunately I'm not going to be able to go tonight, but please head over. Look forward to seeing you early next year. Take care.